Good day, grade 12 chemistry students. Today, what we're learning about again is our last one. We're learning our last thing on rates, anyway. Sorry, 3 of 3. We're learning about collision theory specifically and potential energy diagrams. A little bit more detail. We're going to learn about it now. So, normally, what I would do with this is a think, pair, share. So, just think, and you can't pair or share. Share with your mom, okay? If you're watching this at home. So how does the amount of collisions of molecules in the reaction affect the rate of reaction? Take a moment, think about it. You should have shared with your mom, increase the collisions, increase the rate. Pretty straightforward. So here we go, let's get into a little bit more detail. So the collision theory assumes that particles of a reaction mixture are constantly in motion. They're moving around, whether you see them or not. You look at a beaker, you tell your lab partner, doesn't look like it's doing anything. Well, it is. It's moving around. For a reaction to occur, there must be collisions between the reacting particles. And what we say is the more effective the collisions are, the faster the rate. Now, molecules are held together by bonds. In order for those reactions to happen, you have to input energy to break those bonds before the chemical reaction can occur. So that energy needed to break those bonds is called activation energy. So specifically, mathematically, if we want to find the rate, okay, what we have to do is we have to figure out how many times these things are colliding, okay? So these reactants are colliding, and then we have to multiply it by the fraction of the collisions that are effective, okay? So effective collisions are actually the ones that actually cause the reaction to occur. If you bounce into somebody, you might not hit them very hard, and if two reactants bounce into each other and they don't really hit each other that hard, no reaction will occur. They have to hit each other with enough kinetic energy for them to actually react. Okay, so that's what an effective collision is if it's hitting in just the right way. Okay, if you crash, if you're in the parking lot with your parents' car, you accidentally bump into somebody with your bumper, that isn't like the right orientation and nothing might happen. But if you open your door and slam it into somebody else's car door, if you're parking at the mall, that actually might cause more damage even if it's happening at the same speed. So what I'm trying to tell you is that it matters how the orientation of the reactants when they hit each other. How do they hit each other? Do they hit in the right orientation for a reaction to occur? Are they facing the right way? Are they going with enough speed? These are things that need to be considered. So let's take a look at an example. For us to figure out the rate of reaction, what we're going to do is we're going to look at an example here. And what we have is, this one says we have 1,000 collisions per second, but only 1 in 100 of those collisions are actually effective. So it takes 100 collisions, and every one of them, 1 out of 100 are effective. And every 1,000, there's 1,000 per second. So if you multiply 1,000 times 1 over 100, you actually get 10 effective reactions per second. So when we look at this math again, what cancels out? Well, you take a look, and actually, the collisions will cancel out, and you get reactions over seconds, okay? And if you really want to write out those units, you understand that there's 10 reactions per second, okay? 10 effective reactions where they actually create products. Well, what are the things that we can do to increase the rate of reaction? Okay, well, we can do two things. We can increase the amount of collisions that actually occur. And the way that we can do that, knowing the 5 things that we know, we can increase the concentration of our reactants. More things will bounce into each other. Or we could take our reactants, and if they're in chunks, we can chop them up into tiny little pieces, increase the surface area. Or we could increase the temperature. Okay, remember, if we're in our bouncy castle in our classroom, if we increase the temperature, that means that instead of walking around that bouncy castle, you are running, okay? Like Ben Johnson on steroids around in that bouncy castle, and you're going to more likely to run into each other, okay? Now, we also have reactions per collision, okay? So what can we do to increase every time you bounce into, two reactants bounce into each other? How can you actually increase the number of reactions? Well, you can actually change the nature of reactant. If you change the nature of the reactant to 2 reactants that are more reactive, when they bounce into each other, they're more likely to actually cause a reaction. Or you can add something called a catalyst, okay? Now I want you to imagine a catalyst as something that just allows two of the reactants to kind of fit in the right orientation, to hit in the right direction. Okay? They don't actually get used up themselves, but they just allow the collisions to be more effective. And finally, temperature again can also, it's the one that is found in both, can also increase the amount of reaction per collision because this increases velocity. Okay? It increases the kinetic energy of the molecules, so they're moving faster. They're more likely to run into each other, okay? But they're also going to hit each other harder. So they're more likely to hit each other, causing more collisions. But when they hit each other, they're going faster. They're more likely to cause a reaction to occur. To summarize this in a note a little bit more thoroughly for you, I'm just going to read this off again. So the number of collisions, okay? This depends directly on the concentration or surface area of reactants. The shape and orientation of the molecules help to determine if a molecular collision will result in a reaction. So how they hit each other, okay, their orientation in space, cause the reaction to happen just right. If they hit each other wrong, the reaction won't happen, okay? And finally, activation, it's not finally, activation energy is next. The minimum kinetic energy that reacting molecules must possess in order to react. So this means activation energy, sometimes if it has very high energy, if it needs, like if they have to hit really hard for the reaction to happen, that means the activation energy is very high. If they just have to hit each other just slightly and boom, reaction happens, that's very low activation energy. If you have a stick of dynamite, you don't want to jump on it, okay? Life lesson, folks, don't jump on a stick of dynamite. Even if it's not going to, even if you don't have a flame on it, it has low activation energy. It could potentially, you're jumping on it has enough kinetic energy for it to actually react. And finally, temperature, like we said, has a dramatic effect. Well, why? Well, the reason is because it impacts the amount of collisions and the amount that are actually going to cause a reaction by increasing the velocity. So for the beginning of next class, what I'd like you to do is I'd like you to answer these three questions. So pause the video and see if you can answer it. What is the difference between an effective collision and an ineffective collision? How can we increase the amount of effective collisions? And how can we increase the amount of collisions in general? So answer those questions and bring them to class. So let me show you how I'd like you to draw the potential energy diagrams from now on. And what I'd like you to show me is now we have potential energy right here, okay? We have time right here. This is exothermic. So your potential energy of your system starts greater and goes lower over time. Now previously we just drew a straight arrow. Now a potential energy diagram, when we have to include something activation energy, what has to happen is we actually have to add energy to it. Okay? So we have to add energy until we get to a point, okay, where at this point we call it's an activated complex. It's at the point where it's at its highest potential energy, where there either could fall back to reactants or it could turn into products. Okay? When I mean fall back to reactants, it means you have to supply some energy to this. This amount of energy right here, which we call EA. Okay? And EA stands for activation energy. So we're going to supply a certain amount of activation energy to get this going. All right? So once we supply that, we're right here. And at this point, we're at the point where the bonds of our reactants are broken, and we're forming new bonds to turn them into products. And this point right here is called our activated complex. And so what it is it looks like it's really a theoretical thing, but because it exists for a millisecond, where you have the products are turning into reactants. It's in between, okay? And half the time it will turn into products, and the other half of the time it will turn into reactants. Now, we have to label everything else, so I'm going to do that now. So the last thing that we have to add here is the difference in enthalpy, okay? Now that's the amount of energy I get out. And we call it the net enthalpy because I actually have to put energy in initially. But I get that energy all back when I turn into products. When you light, the activation energy for a stick of dynamite is the wick. You light it on fire, it supplies energy, and boom goes the dynamite. That's right, boom goes the dynamite. Well, you get all that energy, even that energy you put in by lighting that wick, you get that back, plus the energy of the chemicals in the dynamite reacting and turning into gas products, okay? So this is how I would expect you to label this diagram, all right? Let's take a look at endothermic. So this is our endothermic reaction, where we have our reactants and we have our products. And you'll notice that it actually goes above the line. So if I look at this, this is all considered what? Activation energy, EA, okay? It's all considered activation energy because I have to input all this energy to get it above, to turn it into products. Imagine it as if this is an individual, a student in my class. I don't want to say it. I don't want to give it away, but I think you should be able to tell from my drawing. They have hair, dark hair, and they're rolling a bowling ball up this hill. Now, in order to get this to go to products, they can't just roll it this high. If they roll it this high, the ball will fall back down. They actually have to roll it right to the top. And at this point, it either can roll down this way back to reactants or this way to products. So once you get it up to this point, you have a chance of making products. And this point right here, we call, again, the activated complex. Okay? They actually represent it by a funny symbol in the textbook. You can take a look at it. But that is the potential energy diagram for an endothermic reaction. So where's the enthalpy difference? Well, it's the difference between the products and the reactants. That's the amount of potential energy I've actually inputted. I actually have to input this much energy for the reaction to happen, but I actually get this much out. Okay? So think about, guys, if you think about something like, for example, the most famous enzymes in the world, one of the most famous enzymes in the world is chlorophyll. Okay? And chlorophyll actually creates glucose. It takes CO2, takes water. It happens in all plants, and it makes products. Now, you have to supply a lot of energy for that to happen. And you can actually do that in the lab. It requires tons of energy. What does chlorophyll do? What do enzymes do to speed up the rate of reaction? What they do is they lower the activation energy. So enzymes lower EA, they lower activation energy. So once you add a catalyst, what it looks like is something like this, where now your EA, instead of going all the way up to the top, it's easier. So if we're this individual unnamed from our classroom, I'm not saying any names, I don't want to tell them, but that is, again, it's easier for them to push it up that red hill than the black hill. So therefore, because it's easier, it happens at a faster rate. It's easier to roll up the hill, so if they're going to roll this up the hill over and over again, they're going to be easier to do, a lot easier up the red hill than the black hill. And the way that enzymes work, and I don't want to get into detail about this because this is more biology, is essentially they're like lock and keys. They have spots that fit the shapes of reactants, okay? So if this is reactant circle and this is reactant triangle, they will fit into our enzyme. And when they fit in there, the enzyme sometimes will change shape, or it will just allow a pocket for them to touch each other and fall in love, make a reaction. It happens much easier. Without this enzyme, okay, or catalyst, these guys will never fall in love, okay? So what do enzymes do? They lower activation energy. They allow things to come into contact with each other, and so therefore they increase the rate, okay? Boyfriends and girlfriends, guys, the catalyst in your love relationship is Walkerville High School. Without Walkerville High School, you never would have met, never would have fallen in love. And so you should say thanks to Mr. Dreger for Walkerville. And anyways, that's your lesson. Enjoy it, and we will see you guys soon.
My boat